More examples. Limits at infinity of rational function. All of these are rational expressions because it's the ratio of two polynomials. You have a polynomial here of degree 3, a polynomial here of degree 3 as well. Here you have a quadratic polynomial, a cubic polynomial, a cubic function, and here you have a cubic divided by a quadratic function. Okay, so how do we take the limit? So what we need to look at first is to watch out for the degree of the numerator of the leading term. It has to be the leading term, and the degree of the denominator. Okay, and what we do next is we divide each term by the highest degree of the denominator. Okay, look at this. We divide each term by the highest degree of the denominator. So let's look at letter A. We divide each term by the, what did it say? Highest degree of the denominator. So what is the highest degree of the denominator? It's 3. So dividing each term, we get the limit of 2x cubed divided by x cubed plus 7x squared divided by x cubed minus 5x over x cubed plus 9 over x cubed. Whole thing is divided by 3x cubed divided by x cubed minus 6x divided by x cubed plus 1 over x cubed. And of course we can knock out a few terms here in both the numerator and the denominator, and we will have the limit of 2, so, that gets cancelled out. Just simplify each term. That's 7 over x minus 5 over x squared, and there's nothing much we can do. That's still 9 over x cubed. Whole thing will be divided by, well, that knocks out everything, so that's 3 minus 6 over x squared plus 1 over x cubed. Nothing much to do there. And we take the limit as x goes to infinity. And remember, it's just a matter of remembering that the limit of 1 over x to a power, as long as that is positive, is 0. So all of these go to 0. This goes to 0. That goes to 0. Okay. And of course we know that the limit of a constant is equal to a constant. So really what we have here is that the limit of everything, of this whole expression in letter A, is equal to 2/3, because the rest of the term would go to 0. So the limit of this expression as x goes to plus infinity is equal to 2/3. Let's go ahead and think about where the 2/3 came from. You can see that it's the coefficient of the leading term of the numerator divided by the coefficient of the leading term of the denominator. Okay, let's see what is happening in letter B. Again, what do? We divide each term of the highest degree of the denominator. Let's go ahead and do that. So divide each term would mean that we've got the limit of 27x squared divided by x cubed minus 5x over x cubed plus 23 over x cubed. That's 8x cubed divided by x cubed minus 6x squared over x cubed plus 1 over x cubed. Take the limit as x approaches infinity. So let's simplify. That's equal to the limit of 27 divided by x minus 5 over, that's x squared, and we leave that alone, divided by, that becomes 8 because this knocks out, and minus 6 over x plus 1 over x cubed. And then we just examine each term and see what happens when x goes to infinity. Remember that this is a reciprocal, so that goes to 0, 0. Okay, here that just stays the same. and that goes to 0. That goes to 0. So what we have is 0 over 8, and that's really equal to 0. So it seems like, think about it, we want the x to go to infinity. Well, when x goes to infinity, this is a higher degree, which, to think about it, this goes to infinity much faster rate, at a much faster rate than the numerator. So if this goes to infinity much faster than this one, think about it, that means the reciprocal is the denominator dominates, so the whole thing will approach infinity faster. So 1 over infinity would be, the limit would be 0. How about this last example? Okay, so divide each term by x squared because that's the highest degree of the denominator. So we take the limit of negative 7x cubed over x squared minus 5x over x squared plus 2 over x squared divided by 6x squared over x squared plus 1 over x squared. Simplifying each term again, we have the limit of negative 7x minus 5 over x plus 2 over x squared, whole thing divided by 6 plus 1 over x squared. So we look at this and we observe what happens when x approaches infinity. Let's leave this alone first and see how the reciprocals behave. This goes to 0, that goes to 0. And so all the rest goes to 0, and that's just a constant in the denominator. So what dominates is this expression, which means that if this is what's happening, what is the dominant term, this goes to negative infinity because x goes to infinity times a negative, so the limit is minus infinity. So what do we do when the degree of the numerator is greater than the degree of the denominator? We divide each term again by the highest degree of the denominator. We observe that. And then the rest, as the rest goes to 0, we check out the expression that's left and find out what it is. You know, it's an ax to the n term. Then we just determine whether it goes to plus infinity or minus infinity. So let's summarize what we observed from the 3 examples. Here we see that the limit of letter A is 2/3. And how did we get that? When the degree of the numerator is equal to the degree of the denominator, then the limit is just equal to the ratio of the leading coefficient of the numerator and the denominator, so it's 2/3. Now here we said that the denominator has a higher degree than the numerator, so this term, the denominator dominates. Think about it, it dominates the numerator, so it goes to infinity faster. So you have kind of a ratio of 1 over infinity. So when the degree of the numerator is less than the degree of the denominator, the limit is equal to 0. And then here we have the opposite case. The degree of the numerator is greater than the degree of the denominator, and we observe that this is equal to minus infinity from the previous slide, because when everything was divided by x squared, 7x was kind of the leftover, and because the rest of the terms went to 0 or a constant, so we observed what minus 7x, where minus 7x goes, and we said that it goes to minus infinity as x goes to plus infinity. So let's summarize what we did. Okay, here when the degree of the numerator is equal to the degree of the denominator, then we observe that the limit is equal to the ratio of the coefficients of the leading term, a over p. There's A and there's P. Here it's just an example. The degree is 3 on both the top and bottom. Okay, what about letter B? In letter B, the degree of the numerator is less than the degree of the denominator, and when that's the situation, our limit is equal to 0. Okay, and then when the degree of the numerator is greater than the degree of the denominator, then the limit we have to take into consideration when we divided the denominator, every term by the highest degree that occurs in the denominator, and the rest goes to either 0 or infinity, and we just have a leftover term of a to the, minus 7x in this case, then the limit is either plus or minus infinity. Let's try and see how we can apply what we have summarized. So instead of dividing each term by the highest degree that occurs in the denominator, what we do is just look at the degree. So here in letter A. Okay, what's happening in letter A? Both the degree of the numerator and the denominator are equal. So what we just look at is just the coefficient. Take the ratio. We just take the ratio of the coefficient of the leading term. So negative 9 over 3. Right there, negative 9 over 3. That's equal to negative 3. Right? Okay, here we observe letter B and see that the degree of the numerator is less than the degree of the denominator. So right away, we know that the limit is equal to 0. Alright, in letter C, we see that the degree of the numerator is greater than the degree of the denominator. Then we have to determine first by dividing each term by the highest degree that occurs in the denominator. So 4x to the 5th divided by x cubed would be 4. Let's go ahead and make a shortcut. That's 4x squared. X divided by x cubed would be minus 1 over x squared. Of course, 12 divided by x cubed. X cubed divided by x cubed is 1. And then 8x squared divided by x cubed is 8 over x minus 1 over x cubed. And we take the limit as x goes to minus infinity. The rest of these terms either go to constant or 0 except for 4x squared. So that goes to 0. This goes to 0. And that just is 1. It's just a constant. So really what remains is 4x squared. As x goes to minus infinity, 4x squared goes to plus infinity. Let's review. Whenever the degree are equal, we just take the ratio of the coefficients of the leading terms. When the degree of the numerator is less than the degree of the denominator, the limit is 0. If the degree of the numerator is higher than the denominator, this is the only time we divide each term by the degree of the highest degree of the denominator, and then the rest goes to 0. You just observe the leading term here, and it's equal to, in this case it's 4x squared, and you just determine whether it's plus infinity or minus infinity. Now there is something going on about the relationship between the graph of a rational function and its limit as x approaches plus or minus infinity. As in this case, they have the same degree. So what is the limit? We know that the limit is equal to 5 over 3. Now look at the graph here on the right side. The graph of the function, as you can see, it tapers down to this horizontal line. Y is equal to 5/3. So it turns out that as when we evaluate the limit of a rational function as x goes to plus or minus infinity, the limit value is actually equal to the horizontal asymptote of the function right there. Okay, so here in this example, the degree of the numerator is less than the degree of the denominator. So when we take the limit we know is equal to 0. So here, observe that horizontal asymptote is y equals 0 because the graph tapers off to the horizontal axis. So the relationship therefore between the asymptotes, horizontal asymptotes, and the limits, as long as it's either 0 or a fixed number, that's the only time that there is a horizontal asymptote. So it happens when we have that the degree of the numerator is equal to the degree of the denominator. Of course, the limit would be the leading coefficient. Let's call it a sub n over a sub over, say, b sub m, and which is also the horizontal asymptote y is equal to a sub n over b sub m. Okay, in this case, a sub n is 5, b sub m is 3, so the horizontal asymptote is y is equal to 5/3. And on the right side, we have that the degree of the numerator is less than the degree of the denominator. Okay, and then we say that the limit is 0, which also means that the horizontal asymptote of the graph of this rational function is y equal to 0. So whatever is the limit, if it does have a limit, corresponds to their horizontal asymptotes. Now we look at a special case. What do you mean by a special case? Special case is when the degree of the numerator is greater than the degree of the denominator by 1. So I'll give you a few examples to tell you what I mean. Say y is equal to x squared minus x over x plus 1. Y is equal to x cubed plus 3 over x squared, and so on. Y is equal to x to the 4th plus x cubed plus 3 divided by 2 x cubed plus 4x. In each of these examples, the degree is always the difference of the degree between the numerator and the denominator is only 1. So this is just higher by 1 degree from the denominator. So this is an x cubed, that's an x squared. This is a cubic, that's a 4th. So this is the special case. And if that's the special case, what we have is, if we perform a direct division, you apply a division on x squared minus 3 divided by 2x minus 4, what we get is this part of the quotient plus the remainder term. So the oblique asymptote is this line as part of the quotient, and if you come to think about it, as x goes to infinity, this goes to 0, and what's left over is really the line. So the function, the blue curve, approaches the red oblique line. So there's your oblique asymptote. So as x gets larger, the difference between the line, the blue line, and the blue curve and the red line is getting smaller and smaller, and naturally it will approach the oblique line, which is your oblique asymptote. So this is only occurring if the degree of the numerator is greater than the degree of the denominator by 1. Okay, let us summarize what we have been doing so far. In order to do that, let me give some examples so that you know if we have this table and you have an example, then you have kind of a cheat sheet. Okay, suppose this is f of x is equal to 2x squared plus 3 divided by 4x cubed plus x. Okay, so here is a case where the degree of the numerator is less than the degree of the denominator. The limit is 0. And the asymptote is a horizontal line corresponding to the horizontal axis, which is y equal to 0. Let's take another example. Say f of x is equal to 2x squared plus 3 divided by 7x squared plus 5x. So we'll check the degree of the leading coefficient of both the top and the bottom, and we see that for this case they're equal. So when the degree of the numerator is equal to the degree of the denominator, we just take the ratio of the leading coefficients, the coefficients of the leading term, so it's equal to 2 over 7. And that corresponds to your asymptote y is equal to 2 over 7. And then, when we have a special case, say 2x squared plus x divided by x minus 1. So here the degree of the numerator is greater than the denominator by just 1 degree. The limit, as we said, well, we can do it very easily here. If we divide each term by x, then you'll have a 2x here plus 1 over x, plus 1 divided by 1 minus 1 over x. So it has no limit because it's either goes to plus infinity. In this case, it's plus infinity. Let's just say we'll write plus or minus infinity, but here it's plus infinity. And of course, because of the situation, the limit will depend on the slope of the oblique asymptote. So in this case, to get the asymptote, we have to perform the division first. Perform the division, and what you will obtain is a line, a linear expression, plus the remainder. And so the linear expression becomes your oblique asymptote. So how to find oblique asymptotes? The first thing we do is we check the degree of the numerator and the denominator. And it's the case when the degree of the numerator is just greater than the degree of the denominator by just 1. And what we do, we perform the division. And what you will get is a quotient, which is made up of a linear expression plus the remainder. And the graph of the linear expression becomes the oblique asymptote. Let's go back to the previous example, and we take that and do the division. So we let f of x equal to 2x squared plus x divided by x minus 1. Now let's go back to your algebra that you love so much and perform the corresponding division. 2x squared plus x, and I will extend this because you know there are other terms that we might incur. So divided by x minus 1. Now how do you do your long division? Do you remember how you do your long division? 2x squared divided by x, that's equal to 2x. And then you multiply 2x by the divisor, so that is equal to 2x squared minus 2x. And then of course the top minus this second line, that cancels out, and x minus a minus 2x becomes 3x. And of course we take now 3x divided by x, and that's equal to 3, and then you multiply, that becomes 3x minus 3. So let's add a 0 here. That way you know that 0 minus, so that cancels out, 0 minus and minus 3 is 3. So what it is that you have a remainder. So what you have here is that's equal to 2x plus 3 plus the remainder 3 over x minus 1. So this is equivalent to the function f of x. So as x goes to infinity, then this term goes to 0, and so what is left over as x goes to infinity means that the function will approach this oblique line. So your oblique asymptote is the quotient, that's the linear expression, it's part of the quotient, and you just eliminate the remainder. So it is going to be y is equal to 2x plus 3. The end.